All right, hello. We're here to do AP Physics circular motion problems. We're going to do selected problems from this homework set. Let's start with the first one. Problem one says 5 kilogram object moves according to the equation, yada, 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 where x is given position as a function of time. And it says, hey, find the average force exerted on the object from 2 seconds to 5 seconds. And so you were enjoined to think about what average means in general in physics. So the main idea here to me is when you talk about what average means, we say average in physics means an average value is if you had just one constant value for that variable. It's the one constant value that would give you the same end result. Okay. So, for example, if we had last year, we talked a lot about average velocity. And so we said, well, I know, for example, if I had a position versus time graph, and I had some function, maybe something that looked like this, right? And we said, hey, if I look at 2 particular times, right, maybe I look at this time here, and I look at my value here at this time. And you said, well, I know that if I'm thinking about velocities, I know that the slope of the position time graph is velocity, and I could draw in a line that's tangent that just kisses the curve right there, and that would give me the slope of the tangent would be the velocity at that instant. It would be my instantaneous velocity. I could draw in a tangent here, and when it just touches it right there, and the slope of that line would be the velocity at that time, right? And you say, okay, well, that's nice, but what I want is the average. Can I just take the value here and the value here, add them up, divide by 2? Would that give me the average? And the answer is no. We might remember from last year that the way to get an average value here, you might remember vaguely that I would just draw a line that goes dunk, dunk through both points. And the slope of this line would be the average velocity represented with a V bar, right? And the bar means average, right? And you say, no, wait, why does that line give me it? Here's why. Because if I come over here, tuk, 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 that value, tuk, 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 that value. Look, average velocity is if I look at the overall change in position, the overall displacement divided by the overall time, that's the way you get the average value. Well, look, the overall displacement is just, it's the rise from there to there. And the time is just the run from there to there. So if I had one constant rise to run ratio, one constant slope, that would be one constant velocity. That would be the average value. The one constant value that gives me the same result. What's the result? What's velocity? It's changing the position, right? It's the displacement. Having that same displacement in the same time, it would be this one constant rise to run ratio. Does that make sense? So it's that line connected to, and you say it's because it has one constant slope. That slope would be the V bar. Okay, that gets me from here to here. All right, we can do the exact same thing on a VT graph. Couldn't we? We would say, here's velocity in meters per second versus time in seconds. And we would say, hey, maybe I have some, wild and crazy velocity time graph. These are not going to correspond, okay? I have some wild and crazy velocity time graph. Woo! Right? Okay. And someone says, hey, can you tell me what the average velocity is between this time and this time? Right there, and right there, right? And you say, yeah, I mean, my tangential, if I look at this velocity, if I want the average acceleration, okay, that's what I'm talking about, finding the average acceleration. You say, well, acceleration on a VT graph, that's the slope, right? The slope of the velocity time graph. And sure enough, I could draw in a tangent here and take the slope of that tangent, and that would be the acceleration right at this time. I could draw in a tangent here, and the slope of that tangent would be the acceleration at that time. But if I want the average acceleration from here to here, I'm just going to draw one line that connects those 2 points, right? Something like this, right? And the slope of that line will be a bar, will be my average acceleration. Why? Because that's my change in velocity over my change in time, right? You say, look, here's tracking over here on the side. There's the velocity I start with, and there's the velocity I end with. This rise here is the change in v, and this is the change in time. And look, the rise to the run ratio, that's the slope of this one line. And so if I had one constant acceleration the whole time, same slope, same slope, same slope, what one constant value would give me the same result, the same change in v and the same change in time. That is what we mean by average, is the one constant value. So, that was a big background on average and what average means in physics. So getting back to this problem, we have an equation for position as a function of time. We want to know from 2 to 5 seconds what the average force would be. You see, okay, now wait a minute. Average force, right? So now what is it that force does again? As far as like the motion of something, what force does a bunch of things, right? It changes momentum. But in this case, the force is going to do is it's going to accelerate the object, right? As in F equals ma. Now, if this is the average force, we're going to be having a average acceleration. You say, oh, wait a minute. If I could get a VT graph, right, then that slope, So what I'm going to do, they didn't give me the velocity as a function of time, though. They gave me the position as a function of time. So what I'm going to do is I'm going to take that equation they gave me for position. 1/12 t to the 4th minus 1/3 t cubed minus 40t squared plus 4t plus 11. I'm going to get the velocity function from this. So it's an equation. I can find the velocity at any point in time. That's going to be the equation of whatever wacky curve. So I'll go ahead. I'll say the velocity is going to be dx dt. I'll take my derivative. T to the 4th is going to become t cubed. The 4 kicked out in front, that'll be a 1/3 t cubed. The 3 get kicked out in front, that'll make that just a minus 1 t squared. 2 in front, that'll be a minus 80 t, and then it'll just be 4, and it's a constant term, and that's my velocity as a function of time equation. Now, what I'm going to do then is I'm going to go ahead, I'm going to find this point and this point. I'm going to find at 5 seconds, right? What's my velocity at 5 seconds? I'm going to find what my velocity is at 2 seconds, right? And then find the change in v divided by the change in t, and that'll be a bar. And then I just take the a bar, multiply by the mass, I'll have f bar. That's my plan. That's my plan. So what follows after this is just a bunch of algebra. Do you want me to plug in and do all the algebra for you? Don't answer that. You know that you. You know we can do this math. We can do this math. I'm going to cheat and use the calculation I did earlier to just whip through this. If I go ahead and I say, so I'm trying to go from t equals 2 seconds. Should I write on this? This graph isn't the graph of this function. Would it be wrong for me to write on here? Probably. We want to find, so the next step here is we're going to find the v at 5 seconds, v at 2 seconds. So say v at 5 minus the v at 2 divided by the delta t, right? You know what I'm saying? That's going to be a bar. All right, my delta v over delta t. Sorry to squeeze that in like that. Okay, hey, the v at 5, you say, what is that v at 5 going to be? Well, I'll put a 5 in for t, right, and solve through. So that's going to be 125 thirds minus 25 minus 400 plus 4 minus the v at 2. We'll put a 2 in for t. That'll be 8 thirds minus 4 minus 160 plus 4 divided by the delta t. Well, that's from 2 seconds to 5 seconds. That'll just be 3. Okay, so this is going to be a bar. I'm going to skip doing all the simple math here, right? and just say that comes out to be negative 74 meters per second squared. All right, when you do that math, that's what you should get. Okay, now that I have that, I'm just going to take this value, put it into here to get F bar. They told us that the mass of our object was 5 kilograms. And so F bar is going to be 5 times negative 74. And you say, aha, that means F bar 5 times 70, 350 minus 5 times 420. So it's going to be minus 370 newtons. And that is F bar. All right, that's our average force that it took to change the velocity from the value at 5 seconds to the value at 2 seconds. The average rate of change times the mass. So it's the average force it would take to get that to happen. Okay, now, keeping in mind again, could I take the next derivative, get an equation for acceleration, and then, whatever, and then get the two values for the two accelerations? I could. Would that help me get A bar, though? What am I going to do when I have the two values? Like, look, going back to this one, let's go to the simple one here. Hey, if I knew these two positions, well, no, this is this one, sorry. If I knew these two velocities, could I get V bar from this? I can get A bar. Can I get V bar? What would you do? Could I take these two velocities, add them up, divide by 2? That would give me the value in the middle. Would that be the average velocity? No, that's not the average velocity. Isn't the value in the middle? Like, let me just show. If I had a position time graph, right? Maybe my position time graph, I could have just worked with that one. But if I had a position time graph that was some sort of here, look, it's like this, right? You know what I mean? If I took the velocity here and the velocity here, so I just take the slopes, is the middle value going to be like the value right in the middle between? Is that going to be the average? Not necessarily, right? Not necessarily. I'm spending, because if this hooks up rapidly, right? I'm going to have spent more time at a low speed, less time at a high speed. My medium value, the value right in the middle between these two slopes, isn't going to be the average. It's going to be closer to the. Do you know what I'm saying? If I had a graph that looked like this and then hooked up at the end, you know what I mean? My average velocity, I got a really big value here, but I had all this time with a really small slope. You know what I mean? The value right in the middle is not going to be the average because I spent more time at the low speed. You see what I'm saying? And so the only way to get the average is to draw the line that connects the 2 points here. You know what I mean? To get the average slope. You can't just add them up and divide by 2. Okay, because we care about the duration. So that's the idea. That's what I'm getting at. I can't just take the 2 accelerations, add them up, divide by 2. That is not going to give me the same answer. We could prove it here, right? I could just go ahead, take the derivative. Sure, what the heck? Why not? Take the derivative. Hey, whew, what would the acceleration graph look like? Take the derivative. Going to kick a 3 out. That's going to be a t squared minus 2t minus 80, right? And I'll put in 5 seconds and I'll put in 2 seconds, right? At 5 seconds, right? So my acceleration at 5 would be 25 minus 10 minus 80, which would be 65, right? It could be negative 65 meters per second squared. You're saying, what's my acceleration at 2 seconds? Put in 2 in, that would be what? 4 minus 80, right? You say, okay, says it's just going to be negative 80 meters per second squared. If I add them up, divide by 2, right? Negative 65, negative 80, that's going to be if I had those up, right? 65 plus or minus 80, right? Add them up, divide by 2. You say, is that going to give me negative 74? Close, but it's not the right value. This is going to give me off by 15, so 7.5. That'd be a negative 72.5 meters per second squared, and that is not the same answer. It does not give you the correct answer when you do this. Okay, this is not going to do it. Okay, all right, there. That's enough for problem number 1. All right, moving on.